40
Przepraszam. Ja ją zawsze pół godziny wcześniej, że pół godziny.
Tak jak niektórzy przychodzą, przecież to jest zapełnione.
Nie ma żadnego znaczenia.
Jest. Wiedziałem, bo matematycznie nie było.
Szybko,
Czy to jest? Słychać mnie?
Już połamałem, tak?
But I can still switch slides, right?
Sure.
Okay.
Okay, we can start our next talk. It's really a pleasure to present Marek Kaluba. Now it's Karlsruhe Institute for Technology and also associated with Heidelberg University, but you should know that he began his career at our faculty, and I know him from time he was a student of the first course. Okay, the title is here and the stage is yours.
All right. Thank you very much for giving me the opportunity to speak here. Yeah, so when I was invited by Pavel to talk here, I was in a bit of a problem because in some sense I'm not doing topology anymore. So there won't be much topology in my talk. I do apologize. However, this thing that I'm doing algebra. So this is non-commutative computational algebra. However, I'm doing applications. So there will be some applications, even though I will be presenting only the mathematical ones, which in general and others can be applied to semi-definite optimization that inherit some kind of symmetry from the definition of the problem. Okay. So here is a brief outline. I'm going to spend a few minutes giving you a motivation. So what is the problem we are trying to solve? Then I'm going to define the tool we are going to solve it with in semi-definite programming. Then I'm going to talk a little bit about group symmetry and what I mean that the problem is invariant. And finally, we are going to see how to use this group symmetry in an efficient manner to produce a simplification of the problem. Okay. So motivation. Imagine that somebody gives you a polynomial f and asks, is this polynomial globally non-negative? So, for example, if you're running energy network, you might want to say, like demand is some function, supply is some function. I want to make absolutely sure that supply is always much bigger than demand to avoid blocks and appliances switching all and stuff. So you want, first of all, you want a proof, not only like some computation, but you want some proof. And this question is very easy to refute. If somebody says this polynomial is non-negative, I say, no, you're wrong. Here's the point. I evaluate this polynomial and the value is below 0, game over. So what I am actually interested in is some kind of a witness of non-negativity that somebody gives me, and it's easy for me to verify that this polynomial is not indeed non-negative. Okay, so we have here we have two different flavors. Well, I will be talking about two different flavors of positivity or non-negativity. One is the analytic one. I treat my polynomial as a function, And the other one is the algebraic. And I'm doing computational algebra. So here I want to give some structure to my polynomial that will, just by looking at the structure, allow me to say, yes, this polynomial is non-negative. Okay? And we know one structure like this. In the high school, when we have this polynomial, one variable, we know that we don't have to evaluate my polynomial everywhere to see if this is positive or not. It's just enough to compute the determinant, the discriminant, and check if it's below 0 or not. So actually, when you do this, and if you think about function as a parabola, which is just shifted to the right and left and then shifted up and down, this is the same thing as trying to get the sum of squares decomposition. So if I know these two things about the polynomial, I can produce you a sum of squares decomposition on the row. So we say that a polynomial admits a sum of squares decomposition, so it is source, if and only if f can be written as a sum of squares of other polynomials. And here's a problematic example that we immediately hit. It's a polynomial in two variables, x and y of degree 6. And you can prove to yourself, you can use yourself in the back row, this polynomial is non-negative. It's not really, it's really easy. You can know the right thing. But it's not a sum of squares. Okay? So there is a problem with this. So in some sense, we are trying to show more than we actually want, but maybe that's fine. It will be fine for me. Okay, a brief history of what we are doing. This is something called Hilbert problem. And Hilbert asked this problem and then partially solved it, saying the problem says when is a positive polynomial, non-negative polynomial, always a sum of squares. And here is the complete list of cases. It's univariate, or it's degree 2 arbitrary number of variables, or degree 4 and 2 variables. So degree 6 and 2 variables, that's like the most polynomial, might not be the case, and you see this one. Or you trust me. Okay, and this problem was actually solved by Artig in 1924. And basically said a nowhere non-negative polynomial p is a sum of squares of rational functions. This might sound really strange, because I somehow sum up the rational function squared and I get a polynomial. But you can think of this as follows. There is a pure polynomial, which is collects all the denominators, such that if I multiply p by q squared, it actually becomes a sum of squares. And you can trust me or not that if I take the Gaussian polynomial and multiply it by x squared plus y squared, it's a sum of squares polynomial. Okay. That's it about the history, because what we are really interested is how to find sum of squares decomposition. So for example, we can write a polynomial f as a quadratic function of polynomials. So this is a beautiful polynomial, and I can realize f as this vector matrix vector product. So trust me or check it later. There is some degree of freedom. I can pick lambda arbitrarily. So this is a quadratic function of polynomials. Right? So this is how quadratic functions were defined in linear algebra. And such a matrix P is going to call Gram matrix. So if I can diagonalize this Gram matrix and it has only non-negative eigenvalues, so 0 or positive, then this thing is going to be a sum of squares. Right? Because in linear algebra, we know there's a signature of a quadratic form, and semi-positive definite of this matrix means that the negative part is 0. Okay? So that this is this lemma. We are trying to find a semi-positive definite Gram matrix for some sub-basis of the polynomial ring, which realizes f as a quadratic form. Okay? So here is an example. If I pick lambda to be 6, this is the matrix, and I can factorize this matrix using, for example, Cholesky factorization to get this one. And from this one, I can read off the sum of squares. So this was x squared, xy, y squared, which was the basis. And the first one, the first vector is basically this square. And the second one. So Q, like this matrix of P is not unique in the rank efficient effect. We have lots of freedom. I can add whatever I want here in the row space, adjusting weights, and this could be this. Okay, so that brings us to the next topic, namely, probably everybody has seen linear optimization. It means you have a linear functional, you have a set of hyperplanes, you say, I'm bigger than this one, less than this one, to only that hyperplane, and I'm trying to maximize the function. Okay. So there is a similar flavor of this, namely semi-definite programming, where not only I'm giving the set of hyperplanes and the functional that I want to optimize, but I'm also given some matrix of my variables that I want to be semi-positive. So I'm intersecting this cone, this polytope with a cone of P. So here's the next textbook formulation. I have some functional. This is vector. P now I consider as a vector, so it's a dot product. It's the standard value of the functional. And then here I consider P as a matrix. So I say, P is semi-positive definite. And then I have a bunch of linear constraints, basically saying, dot product with some vector or some matrix, and P must be greater or equal than BI. Okay, BI is a vector. B is a vector of different number. Okay. Okay, so here is an example. How does it translate to the polynomial setting? This is the same polynomial. It doesn't matter really. And we are trying to say, well, when is this polynomial negative? Well, if we find the sum of squares, it will also imply non-negativeness. So it's a sum of squares relaxation. And we are looking for a positive semi-definite matrix P, which can realize F as a grounded. So what is the semi-definite problem here? Basically, this X, I told you that this is good enough with basis. And now this xt is all possible product of monomials. So dots here means it's symmetric. I'm going to write it out. And these vectors of matrices just pick the appropriate monomial from this matrix. Okay? So for example, a to the third power and y I can obtain in two different ways by multiplying x squared by xy or xy by x squared. Okay? So that's what it's saying. And of course, here I said something about functional, but here I'm only interested in the feasibility. So the functional is 0. I'm just interested in the existence of something. So far, so good. Great. And this picture, as beautiful as it looks, slams into a wall pretty quickly. Because if I have n various polynomial of degree 2D, it must be even, right? Then the number of all possible monomials that I need to consider. So in this example, I just gave you the basis, but you don't know what should be the basis, right? So in principle, you should take all of them up to certain degree. And this number grows pretty quickly. And also, when I look at all possible products of monomials from my basis, it also grows even quicker. And that means that I have a lot of variables and even more constraints. Okay? So up to n equal to 1000, you're maybe able to solve it using zero point method. Maybe up to 2000, there are some other solvers like alternating direction method of multipliers that allow you to somehow approximate it, but sooner or later you're going to slam on the wall of computational PDB. And people, invent very creative ways of trying to solve such a problem. But the biggest problem is that we are trying to solve too big a problem. Okay, so let's, instead of trying to be clever after we were stupid, let's try to go back one step and say, oh, maybe I don't need to solve that large problem. Let's try to simplify it before. So this is what this talk is about. What I want to say is that under some conditions, this matrix P can be realized not like a full matrix, but like a block diagonal. And one way of doing this is through chordal decomposition, which exploits the sparsity and the constraint. But what I would like to tell you is invariant decomposition that is derived from group symmetry. In some sense, what I'm telling you now is like an old history from 100 years, mathematics. Okay, group symmetry. This is our optimization problem. I want to say that group G is a finite group, always. And G acts linearly or orthogonally on the space of variables. Okay? Space of variables, space of monomials. Okay? And G acts linearly and orthogonally on space of constraints. So again, we said that each constraint was also defined in the polynomial space by some monomial, maybe of larger degree. So one action is good enough for our case. Okay? And the question is, where can I assume that there exists under this action an invariant solution? So a clear way of saying what is an invariant solution, just take any solution and then average over a group. Okay? Take a centroid. So when is, if P is a solution, when this guy is a solution? So first of all, I want to know that the objective value is the same. Okay? So for this, I need to, well, it's enough if I assume that the objective function now is invariant under the GF. Okay? The second thing is that I want the invariant solution to be semi-positive. Okay? And if you look what is happening, if I'm acting on linearly on the variables, I'm acting on P by conjugation. Okay? So if P was positive semi-definite, its conjugation is going to be semi-definite, and then the set of P and D matrices in the code, so this is a solution. Okay, and the last thing is that I want these constraints to be satisfied. Okay, still for the new solution. And you have to work a little bit. This is not if and only if, it's a sufficient condition, namely that this this vector B that defines the constraint is constant on the orbit. Okay. So what does it mean? This might sound pretty abstract, but what does it mean? On an example, I have this polynomial is Robinson from Robinson form. This polynomial is invariant under the following two operations. I can permute the variables, right? These two come in pairs. This one maps it to itself, and one is also maps to itself. And because every degree is even, I can throw in a minus, and it's going to be equal. Okay. So this polynomial is invariant under these two operations, and these two operations generate a set of asymmetries that I give you. And what I said before, symmetry of monomials like this gives you a symmetry of constraints, because every constraint will be defined by a monomial, and symmetry of monomials giving you the symmetry of the PSB matrix E here. An invariant problem here means that the polynomial is just fixed under the action. So it's very easy to check if I'm looking at an invariant problem which has invariant solution. And now if it has, then I would like to derive some structural simplification from this. And this is a misleading quote of the day. And the structural simplification I can derive from this symmetry is independent from the optimization problem. Okay. And yeah. It's a misleading quote, so I need to explain. Okay, so a little bit of well, theory or facts about linear actions or finite groups. You can switch off if you don't like this. It's not going to impact your understanding of the rest. So whenever G acts linearly on a space, then we say that a G invariant subspace is irreducible if it is if the only invariant subspaces of the space is the null space and the space itself. So it's like a primal building blocks of G spaces. If we act via group G linearly, there are only a finite number of types that the action can look like, irreducible types. Okay? That's the second fact. And the third fact is that an equivariant map, so a G map between subspaces of different types, is necessarily zero. So these types are orthogonal.
So linear.
Yes.
They are non-linear.
Okay, and now we have to think that this matrix N is the one given by the action, and P is the one that is invariant under the action. Okay, so being invariant means that the conjugation of this matrix is the same P. Okay? So if we can assume that N can be decomposed into two such orthogonal subspaces, which are irreducible, then if these two ones are of different type, then P has very specific form, namely its identity and the other sum with some scalars. Okay, so in some sense, then I can know that P can be compressed to just two numbers. And the second fact is what happens if they are of the same type. Then the identity matrix is always the same because it's the dimension, the identity, the dimension of the N1. But I have in total 4 different scalars. So it's a tensor product of identity with something like that. And when I said that there's a finite number of types, I can always take a linear G space and subdivide it into subtypes, which will be orthogonal. Okay? So there is this miracle, if you think about this, if you've never seen this, that whenever a group acts, these matrices that are given by the action can be simultaneously diagonal. We are always in this position for all the matrices given by the action. Okay? So it's a picturesque, if I get there. So it's a picturesque description of the process that we are doing. So we have this invariant under group symmetries. So that means it's in this form for every G. So that means a block-diagonal structure. So yeah, it's hardly visible, but this is our space. Okay? And this is our PSD matrix. And now we know that we can divide this into blue type, green type, and red type. Okay? And therefore, by this lemma, we know that because of the types are orthogonal, we know actually that we can also diagonalize this matrix. Okay? So instead of going to one big one, we have a sequence of small ones. Okay, so here is a quick example. Is this an example? Yeah, so first let's go through an example. So here, yeah, I'm talking about this, but all of this is implemented in the factor that we're using for our resetting. So this is like a running code. So this is something that you can start using immediately if you know what the action is on the problem. Okay, so here is the problem that we have this symmetry group of 4 letters, and This group acts by variable permutation, so it permutes variables from x1 to x4. And the basis is the basis of all monomials of degree up to 2. There are 50 of them. Okay? So when we ask for symmetry adaptive basis, we get this decomposition into 3 blocks. These 3 blocks are given by the truly invariant ones. So these are the symmetric polynomials. But there are also ones that come with some kind of symmetry. So this one, the polynomials are permuted inside the subspace. So we went from 15 by 15 PSD constraint to 4 by 4, 9 by 9, and 2 by 2. And here I said that these projections, so projections onto these subspaces, they live in a group algebra in a basis free form. So here I give you a base form projection. So they have basis because you picked one, in the basis of monomials. But if you pick a different one, they are going to change, and these projections are not going to change. Okay? So what do they look like? Okay, so they live in group algebra, which in principle you should think as finitely supported functions, but if you write them like this, you can think about them as non-commutative polynomials. Okay? So instead of variables in my polynomial, I put numerals. So if I want to add these such 2 things, I just add coefficients accordingly. If I want to multiply 2 coefficients, I just do, well, convolution, which basically means you multiply everything by everything and then you collect. Right? Like polynomials. Let's see another example, I think. So you can check for yourself. This is how you do it. And the projections onto those isotypical spaces, so the spaces of the same type, they live in the group algebra as projections. So projection here means that just p squared is equal to p in a matrix free form, because this algebra doesn't know about the basis of this problem. So for example, this guy, so this subspace with the chosen basis corresponds to this projection, which is 1/2, 1/12, and this is 2 identity minus permutation 2, 3, 2, 4, 3. So this is like a long expression that they just put in 3 long. You can verify through some previous computations by hand or running it to a computer, but this guy is a projection. So p squared is equal to p. Okay, so I can compute them without knowing anything about basis, and then only at the very end, the given basis, I can count to get the matrix projection. Okay, but there was the second part of this lemma saying what happens if I have these irreducible ones that are of the same type or different types, right? So different types, we know that they are orthogonal, so we know that there are zeros here. But now we know that each of the blue type, so this is a subspace of blue type, and now we know that it's just composed of several of blue irreducible. Okay? So that means that I can decompose this as a d1 by d1 blocks. Well, here is 3 by 3. And what did this lemma tell us? That this whole matrix here, even though it has plenty of space, from each of the blocks, it's enough if I pick one scalar. Right? It is a tensor product of identity. So each of the small blocks is identity up to a scalar. Okay, so this 3d1 by 3d component can be actually projected to literally 3 by 3 matrix. Okay? It's only the multiplicity of the blue irreducible that is important, not its degree. Actually, because of this, we want the degree to be as big as possible. And so if you know something about representation of finite groups, that means we want as non-abelian group as possible. Okay, so for example, we started with this B3 space that actually turns out to be a direct, well, consisting of 2 irreducible ones. So instead of 2 by 2 matrix, now I'm actually looking at 1 by 1 matrix, one projection with 1 by 1 substance given by this polynomial. And again, to realize this projection in the group algebra, I take the old one, which projected into either typical summon, and now I take a new one, which is of this form, and this gives me precisely the projection into the single block. Okay, so here's an open problem, because somehow I found this projection, but I actually don't know how to do it in general form. So if you're interested in computation with finite groups, like Kelvin, for example, is, and you can do it like with that or something else. And here's this problem. I have this atypical projection, which is essentially a character of a group of the representation. How do I find a projection field which realizes this this geometric picture, which translates to algebra by saying that the value of P of Q is equal to 1. Okay. So I have written some brute force algorithm that works in the case that I'm interested in. And I'm fine, but it's actually pretty nice. I would be really interested to produce a general statement. So of course somebody who knows a little bit about representation theory of finite groups is going to tell me that this is not possible all the time, and that's true. If your group is abelian, for example, there aren't enough projections in the blueprint. And if your group is non-abelian, as I would expect this to be, then this is actually possible because I can find it. So the question is, when can I find them? And the question is, how do I find them? Okay. And because I said that this is okay, so here is just the same code, but now we change semi-simple to false, and we get this this new basis that is projecting to these possibly minimal components, and we reduce our problem from 15 by 15 to 4 by 4, 3 by 3. How does it scale? Where is this problem coming from? So with this problem, why we started working on this comes from a problem in geometric group theory, when we want to estimate spectral graph of a group Laplacian. And basically it translates to the following statement. So this is a Laplace operator that if I can prove that this expression, so delta square minus lambda delta, is not negative in the positive sense, which I translated to be a sum of squares of elements in the group algebra, then this whole interval between 0 and lambda is not in the spectrum. So we have a lower bound estimate for the spectral map. Okay, so by the way, so here I used the fact that monomials and blah 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 is commutative, but this Laplacian actually sits in the group algebra of the group, so it's a sum of squares optimization over a group algebra. It's a non-commutative setting, but the whole theory I gave you the whole setting. So recently I've been working also with some quantum information physicists, and we are doing similar problem when we try to find a norm of an operator that will give us bell-like inequality. Okay, so we have this problem, and this problem was translated to a semi-definite optimization problem with PSD constraint of sizes 4,000 something, which is not numerically feasible to. It's not even the question about time. It's not a question about the size of memory or the number of cores you have. It's numerically not feasible to solve because the numerical problems are going to be PSDs. And it has 11 million points. Okay, so after making use of a pretty large group of symmetries, and after this symmetrization I described, we ended up with 29 blocks. The largest one was 58 by 58. and only 7,000 of them spent, and I can solve it on my laptop. You have some reference. And to put this into some picturesque perspective, so this is this largest 58 by 58 block. You have a bunch of all smaller ones, everything outside the diagonal is 0. So this is what we are optimizing, and this is fast. And this is the size of the original ESB constraint, and this whole big matrix, and we just project it to the small square. That's it. Thank you very much.
Any questions, comments? So, if not, thank the speaker again. I do hope that we can start without any technical.